So I want to hand it over to Trevor. And again, I wish I'd done a better job, but I'm real excited to have Trevor here. So take it over, Trevor.
All right, here we go. Let's see how this works. All right, can we see that? And all right, can you see my mouse right now?
We can see your slides. I don't know if we can see your mouse or not.
Okay, all right, and you can hear me, right? So we're all good. All right, so as Bill said, thank you, Bill, for the introduction. I'm Trevor Durning. I'm a fourth-year undergraduate student at Columbia University. I study environmental chemistry and sustainable development. I'm a double major up here. Today, I'm just going to talk to you about particulate matter 2.5 and below in South Jersey, community air quality monitoring, and how the high-split computer modeling software can inform an air quality monitoring system. So a little bit about high-split. You'll see that logo down here. It was created by NOAA in about 30 years ago. And the reason why we know it works, and I'll show you the models in a second, is because they released particulate matter into the air somewhere in Ohio. They predicted using the modeling system where it was going to be. And then they used a sensor and a trap mechanism and made sure that it was this thing. And they made the correlation and said, okay, this works. And now 30 years on, the math is extremely complicated. And that's why we use this system. So let's show you a little bit. Let's see if I can move forward here. So here is where I put up a sensor. So what happened with my research is I would go home and we have some cars that sit at the house, and I would notice there was a layer of dust on them. And I attributed it to agricultural PM. I started PM as in particulate matter. I started and I put up a sensor and I started to just monitor events that were happening. And you can see the monitor right here. It's a purple layer. And then you can see the house surrounded by agriculture. So I started to just model the atmosphere thinking that I was looking at particulate matter from agriculture. I did a lot of research on agriculture, and we can just go through a couple more slides here. I'm not going to bore you with this kind of stuff. It's really technical. Some of these things you'll see, this shows how long a molecule will stay in the atmosphere for. So this is toluene, 1.9 days, xylene, 20.3 days. And these are all released from petroleum petroleum refining and petrochemical industries. That's what the paper down here says. So if you ever are interested in reading any of this stuff, just go ahead and screenshot it. And then if you need help finding the papers, I can help you find the papers. But this is just to let you know, this is just to illustrate a little bit of the chemistry involved more. This is just nitrogen in the atmosphere. So if I go back, I'm going to go back one slide. You can see these are electronegative elements and hydrogen, and there's a lot of chemistry that goes on with these. And this is carbon, and each one of these spots is the carbon. So these are hydrocarbons that are released, and these are all in the atmosphere. And depending on what else is in the atmosphere, or the light radiation in the atmosphere, the temperature, the humidity, any sort of meteorological inputs, dictate which direction these compounds go. So you can see here, we've got traffic, industry, and power production. On the left side, we have agriculture. This is ammonia, nitric oxide, and nitrogen dioxide. They get transported and dispersed through the atmosphere, and then they go through different changes. And then they eventually get deposited onto the ground at either a dry, wet, or dry state. This is just different things. I'm going to move on to the next one. Again, nitrogen in the atmosphere. What I like to show with this one is you can see the light radiation here. Here we can see a change in energy. So what will happen is those molecules will receive energy from the system, and they will rotate in such a way where they go to a lower energy state, and then they release that energy into the system. So this is all different things that could happen depending on the meteorological inputs and, where they are on Earth, pressure, right? And volatile organic compounds here, anything with an R is a radical. And this is just another way to show you that these reactions are either forwards or forwards and backwards, depending on, even these are just acid-base reactions right here. So that would be based on the acidity of the atmosphere. And then one more slide about the science. I'm not trying to bore you too much, but this is something, this is surface chemistry, and this is a study they did in 2015 in Nanjing. It's a new particle forming event. So these particles can grow in size based on what these people have dictated as a stickiness factor. But if you think about how big a particle is, the bigger it is, the more water is on its surface. And depending on if there's a lot of particulate matter in the air, they can clump up and become and make bigger particles. So obviously this isn't good for people's health, just breathing in larger particles, right? So what does the EPA give us? The EPA gives us the AQI standard here, and we can see it goes from 0 to 300 and higher, but I believe they say 500 is usually what they go to. And today I'm going to show you a purple event here and a yellow event here. So you basically just think of this as like a yardstick of the amount of particulate matter, the concentration of particulate matter. And I also want to point out that to our phones, we get alerts, anything that's 100 or above. So anything in this area is what you're going to get an alert from. So that's why I'm going to show you this one, and then I'll show you this event. And I'm sure you already know this, but this is what the sensors from the EPA look like. They're like $44,000. These are their monitoring stations. And I'm using that little purple air sensor that you saw and a computer from 2011 that I put some RAM in and souped up a little bit with a solid state drive. And I'm doing very similar work to what they're doing. So I'm like, okay, they've got these great sensors. So now I'm still interested in agricultural particulate matter. I'm at the beginning of my research. And I go to the AirNow website, just like the EPA tells me to do. And I see this. So this is my house. And then these are the sensors that I use to confirm my data, but they're pretty far away. And I just want to point out on this map, just look at the giant unmonitored space from the EPA. I was really surprised by this. I think, I'm very fortunate to be in the situation that I am in my life. And the fact that I went in and tried to look at my own area and I couldn't, it really felt like an injustice. I couldn't believe that I couldn't, my research stopped right there, right? So I couldn't imagine being a family that doesn't have the means that I do to be able to come to Columbia and learn something like this. And just the injustice that I feel is, I'm very lucky to be in a position that I'm in. And I couldn't believe this when I saw it. So I went into the New Jersey Air Quality Report to try to figure this out. And I see that Clarksboro has an air monitoring station, which, is closer than the other ones. And I look and it says ozone PM 2.5. So then I go in and I look at the AQ report to see, what kind of data they're getting from that station. And it's only a filter-based monitoring station. So someone has to go in, remove the filter, and then they essentially run spectroscopy on it. Maybe they weigh it, they do whatever kind of research they do on it, and they figure out what's in the air. Well, I don't know if you guys know, and I would love to hear at the end of this, if you know any information about this, but I don't know when they're pulling it. So the data isn't really accessible to me and isn't really accessible to the communities that need it the most, from my knowledge. So I'd love to hear more about that. So now, here's the purple air map. Here's my house again. This is my monitor right here. And you'll see some of the other monitors in the area. But I didn't place these monitors, so you'll see some of these monitors don't really conform to any data. I think it's just because they were placed. So really, when it comes to something like this that I see, I have to take it with a grain of salt because it's not standardized, right? And I know that in Chester, I know that there's this industry here just from going to the Philadelphia Union soccer games and driving over the bridge and seeing everything, right? So I really would like to get more information about maybe this area, and we'll talk about it. All right, so next what we're going to do is we're going to look at the wildfire event from June 6th to June 9th, okay? So this is what the purple air spits out at me, all right? I've got humidity and temperature in orange and blue, and as you see, they vary throughout the day. They cycle with the day. And then gray, yellow, and blue are different algorithms that I run my data through. And these have been tried and tested over time. So I need to know which algorithm to use. And I'm supposed to look at standardized sensor that in this case would be an EPA sensor. So I have to look at the ones across the river. So we're going to look at this number right here. It's averaged over 24 hours. So it's not going to be as accurate as we need it to be. Okay. I can have very high resolution cases, but I have to use their data that's averaged over 24 hours. So we're going to look at this number right here. We've got 211, 198, 198, and 199. Okay, so we're going to go back into our data. I look at it. I say, you know, I could maybe use this yellow, average everything out on the daily, but I'm just going to use this gray for this presentation. So it's going to be the PM. So that's the one. And now we're just going to walk through time. Here we are at 3:20 on the 6th, and I've got these models shoot out. So I'm going to try to, let me do this right here. Has anybody ever seen one of these before? Has anyone seen a high split model before? No? Okay. All right. So this is what the high split model spits back out at me. And let's try to talk about it a little bit. So each one of these grids, okay, on the map is a mathematical equation. Okay, it's three-dimensional. It's more than three-dimensional, right? It takes in velocity, acceleration, all the different meteorological data for the area at the time and how they influence each other. Now, on the left, we have a back trajectory. On the right, we have a back concentration. So on the left, think of this as the avenue of most likely approach for a particle. And on the right, think of this as just the probability that a particle came from that area, all right? Here, this is meters above ground level. So this is where in the atmosphere you are height-wise, okay? And then you can see the distance. So this is at 3 p.m. You read it from this point forward. Sirius thinks I'm talking to her. So it travels this direction back towards the star. Here again, backwards here. And then if you want to read this, you go from right to left. Okay. And then this is going to be, it looks like I did a 15-hour projection. So this will be 15 hours beforehand. And this will be time now. And this is just to show you where we are in the day. All right. So we're going to keep walking through. Here we go. Now we're here. So now we're at 2240. So 1040. And we can see that the velocity of the particles increased and the probability of the concentration also increased. So we see, based on the data that we see, let's go actually back one, we can see that an event's about to happen. So I model just before the event, and then I'm going to show you a cool thing that I worked a little bit hard on. That way you can visualize a little easier. Here we go. So this is, I believe I might have done this over 25 hours, but we're going to take a look here. So boom, boom, right? So this is over 25 hours where that particulate matter came from. And this is, lower resolution than another case I'm going to show you. But I just want to show you how we can monitor how the atmosphere is moving further in time. Really high concentration from far away, right? So we can tell these particles have a lot of velocity. And how can I see this? I can zoom out. So I go ahead and I zoom out, and then we can see 800 kilometers in 24 hours. A little less than 24 hours, 20 hours it looks like. So I ran multiple particles through this processor essentially, and it showed me all the different heights they could be at and how far they all traveled from, and we can see a pretty clear avenue of approach for that particulate matter. Still further in time. Now the velocity is starting to lower, right? Start to get a little lower. Still through time. Now we just see that whatever this particulate matter that's meeting the sensor is just sitting over top of Pennsylvania. So if there's any industry there that's releasing particulate matter or gas or any sort of byproduct, it's going to react with this particulate matter in the air, probably, right? We don't really know exactly what's going on, and that's kind of where the science is right now. But tracking it and understanding something's happening there is like the big piece right now. That's what we're working. And here we are again, and you can see, so I can, model the trajectories, show you the concentration, figure out where the particulate matter is coming from using this system. And if we knew more about the particulate matter, I can model it better, right? More efficiently, more effectively. Here we go. We can still see more. This was a pretty big event. And then I like looking at the other side. Now we can see we're after the event, and the trajectories are starting to come back in. So we see the velocity is lower. We can see there's some sort of there's maybe a high pressure system in this area that's not letting the particulate matter get in. And then we see how it kind of muddies up the image and how we're really just pulling particulate matter from a more localized area. Okay, and what I want to say about these wildfire events is when we see a trajectory like this and a back concentration pathway like this, and there's obviously a fire alert in Ottawa, they have great monitoring system. We see a lot of particulate matter come in. We see a heavy concentration of particulate matter. But the same type of particulate matter, the wildfire particulate matter, it will linger down the coast as well. So it kind of muddies up the data for higher resolution cases. But understanding that this particulate matter is there helps identify more localized events. So now I'm going to bring it into a high resolution case that I found on September 17th. All right, so I threw everything into a scatter plot, and I, try not to look at any of these outliers that we have in the data here. Try to look for some confirmation, and I see that multiple models are spitting out information around this area. So I took the top marker. I said 85.5. Well, it's not high enough to get an alert to my phone to know this is happening. Let's take a look at it. So I pulled the 10-minute average data from my Purple Air device, and I threw it down into a higher resolution graph, and I can see an event happen between 3 and 7 a.m. And so what does the EPA tell me to do? The EPA tells me to go to the Air Now site. So I pull up the Air Now site, and remember, this is where my sensor is. I should have put a little house there for you. And there's a bunch of green, and they're just saying nothing happened that day. That day was a great day. No issues found. Let's move forward. Well, I wanted to see what's up. So I threw the data into a high split, and this is what it shows me. This is just before the event. I'm seeing higher velocity trajectories that are higher in the atmosphere coming from this direction, a slower velocity trajectory coming from that direction that's lower in the atmosphere, and I see a back concentration pathway just before the event. And now we're going to go to, at the second peak of the event, we see clearly that I'm getting the air that back on this slide. So let me show you again. This is lower in the atmosphere, higher in the atmosphere, a larger concentration coming from a further distance, right? And then I pull back over here, and it stops right there. So clearly the data is not high resolution enough. And then we're going to go to 8 p.m. And this is pretty much how these smaller events go that I keep finding. We get the air from near Dover, it comes in, it's really dirty. And then the ocean air comes in, and it's the dominating force in the atmosphere. And we see how the trajectories change. And that's pretty much what I'm doing. I'm just modeling atmosphere, trying to figure out when the particulate matter is there. So I figure, like, what's next, right? Like, where else does my research go? Obviously, having a network of sensors will help you track, like, a particle front, or if there's what's called cloud condensation nuclei, which means, there's these particles that are gaining water and they're becoming bigger and they're obstructing our view or obstructing health. We've also got an air sampler that can take in samples of the air, and then I can run spectroscopy on it, figure out what it's made of, and then I can more accurately model the atmosphere. And then this one's for gas, any sort of gas. If someone's smelling gas, you can go ahead and pick up the gas signal. So yeah, so I've got my email right down here, tjd2148@columbia.edu. If you have any questions, let me know. I'm always open to talk. There's a bunch of others. If you really want me to get nerdy on you, I can. And yeah, that's what I got for you. There definitely needs to be more air quality monitoring, especially for, people that can't do what I just showed you, and I felt an injustice, just the fact that there weren't better air quality monitors near me. So